Hello. We say that the limit of a function f at x null is L if, for any epsilon, small as we wish, exists a small delta neighborhood around x null, such that the values of f are close to L, and the distance between the values and L is no more than epsilon. Notice that the actual value of f at x null is irrelevant to the value of the limit, and f may even be undefined there. Graphically, for every red sleeve around L, we need to find a green neighborhood around x null for which all the values of f fall into that rectangle. Recall that we have an equivalent definition of a function limit using sequences due to Heine, which says that the limit is L at x null if and only if for every sequence that tends to x null but not actually attains it, we get that the sequence fxn tends to L. We also have a notion of one-sided limit of f at x null. The limit at x null minus is the left limit, meaning that when we are given an epsilon, we need to find a left neighborhood of x null to fit to the definition. Similarly, for the limit at x null plus. When using sequences, the left limit is obtained by taking into account all the sequences that tends to x null and also less than x null. Similarly, for the right limit. It follows from the definition that the two-sided limit, the regular limit, is L if and only if both one-sided limits are L. When the limits do exist, we have a few arithmetic operations that we can apply on both f and g. Multiplication by -1, or by any constant, addition, multiplication, inverting a function as long as the limit is non-zero, and we still have the rule for multiplying a bounded function with a function that tends to 0. Since the limit of a function and the limit of a sequence is basically the same, we can use the sandwich and the pizza theorems on functions as well. We will see example for that soon. Technically, when the function is not bounded, it diverges, but we do have a notion of a limit that equals plus or minus infinity. The limit is plus infinity if, for any chosen bound m, there is a neighborhood such that all the values of f are bigger than m. Equivalently, if all those sequences tends to infinity. The limit of f equals to infinity implies that the function is unbounded, but not every unbounded function at the neighborhood of x null have a limit of infinity at x null. For example, consider this interesting function that is defined in one way on all the non-zero rationals and 0 otherwise. The function is unbounded at every neighborhood of 0. However, the limit is not plus infinity. Why? We can find two different sequences that approach to 0. One with rational numbers and the other with irrational numbers. Convince yourself that in those two cases, the limit of fxn is different. Another example. What is the limit here? Using the sandwich theorem, we conclude that the limit is 0. The sandwich theorem is a powerful tool. It proves existence and the value of the limit with one shot. The family of functions that are defined differently on the rationals and the irrationals are important in order to generate various of counterexamples to common misconceptions about limits. They all come from this basic function that is called the Dirichlet function. That function does not have a limit anywhere on the real line. What about a limit when x tends to infinity? It is L if for any epsilon sleeve we have a bound R for which the values of f fall in that sleeve as long as x is bigger than R. Heine would say that the limit of f(xn) is infinity for any xn sequence that tends to infinity. Finally, we have a notion of a limit equals to infinity when x tends to infinity. We need two bounds here, one for the values of f and one for x. As always, Heine captures that scenario elegantly. For a continuous function, the value of f at x null is relevant, and it must be equal to the limit. That is why continuous functions are good when visualizing limits by sketching a graph. Lucky for us, most of the functions are continuous, and we can apply different manipulations on them without ruining the continuity. Something weird has to happen in order for a function not to be continuous, like division by zero or pasting two functions together without much care. In many cases, even when a function is not continuous, we can still visualize the one-directional limits. Take this function, for example, and sketch the graph. Now it is clear that the right limit is 1. What about this example? The limit does not exist. We can either pick two sequences for which the limit of f(xn) does not agree, or we can sketch the graph and see that the curve behaves weird around 0. Another example, the limit here is 0, since we have a function that tends to 0 multiplied by a bounded function, or we can visualize by sketching the graph. The lesson continues in the next video.